All right. Welcome, everyone, to the first deep dive in our brand new series.
Yeah, this is going to be awesome.
We're so excited to be kicking things off. So the basic idea is you bring us the topics that you're wrestling with, those things that feel just an overwhelming amount of information, and we break them down.
Yep.
We extract the crucial insights, the core ideas, the key takeaways,
We're going to be your guides.
so you can get up to speed quickly and efficiently.
Quickly and in a fun way. That's what we're hoping for, at least.
Yeah, that's the goal, right?
Absolutely.
So think of this as your express lane to understanding all that complex stuff out there.
The stuff that you wish someone had just broken down for you
Right.
without having to read a whole book or listen to a 10-hour lecture.
Precisely.
Yeah. We're going to try and condense it down to something you can digest pretty quickly.
For this very first deep dive, we are going to tackle a topic that might sound a little technical at first glance. We're diving into the world of vectors.
Vectors.
Now, whether you are involved in fields like engineering or physics, or if you're simply curious about how the world works.
Yeah, I mean, this is one of those things that it's like, oh, it sounds like a math thing.
Right.
But it's really not just a math thing.
It's everywhere.
Vectors are fundamental to understanding physics, engineering, even computer graphics and things like that.
Yeah, and we're surrounded by forces.
Right, exactly.
All the time, constantly. And vectors are how we represent and understand those forces.
Yeah, the language of forces.
Yeah.
That's what we're going to be speaking today.
That's it.
The language of vectors.
So our mission today is to really build that solid, intuitive understanding of vectors. We're going to explore what sets vectors apart from ordinary numbers, how we visualize them,
How we talk about them.
how we talk about them, and the basic ways we work with them mathematically.
It's all about laying the groundwork.
Yeah.
Right.
Yeah.
This episode's about laying the groundwork. If you want to understand why a skyscraper doesn't just collapse,
Or how your GPS.
or how your GPS knows where you are,
Yeah.
these are all based on understanding vectors.
It all comes back to vectors.
Yeah.
Okay, so we're looking at this material, and it starts off with a really crucial distinction: scalars versus vectors. So what's the core difference that we need to wrap our heads around right away?
The most fundamental difference is direction.
Okay.
Scalars are just a size, a magnitude.
Okay.
Think about your weight or the temperature outside,
Okay.
or the time. If someone says it's 25 degrees Celsius, you know exactly what they mean.
25 degrees Celsius.
That's it. There's no direction to it.
No duet.
It's just that amount.
Got it.
Vectors, on the other hand, have both a magnitude, like how big they are or how strong they are,
Okay.
and they have a direction, which way they're pointing. So a simple example, imagine you're pushing a door.
Okay.
You're not just pushing with a certain force, you're pushing in a certain direction.
Right.
Both of those things matter, the how hard and which way you're pushing.
Right. Right.
That's the difference between a scalar and a vector. Scalars are just the how much, and vectors are the how much and which way.
Makes sense.
Mm.
So if I'm talking about how much coffee's in my mug,
That's a scalar.
that's a scalar. It's just a quantity.
Exactly.
But if I'm talking about the force I'm using to lift that mug,
That's a vector.
that's a vector.
Because you're lifting it up.
I'm lifting it up.
There's a direction.
A direction involved.
Yeah. And because of this directionality, we need a new set of rules to deal with vectors. It's not just plus and minus and divide like you do with scalars.
Right.
We need what's called vector algebra,
Okay.
a whole set of rules to figure out how these things combine and how they interact.
So visually, how do we represent these vectors?
Yeah.
And what about writing them down? I noticed the material has a few different ways to do that. What are those?
So visually, an arrow is your best friend. You've got a pointed end, which we call the tip, and the other end the tail.
Okay.
The length of the arrow, that tells you the magnitude. So a longer arrow means a stronger force or a faster speed.
Got it.
And of course, the way the arrow is pointing, that's your direction.
Makes sense. That's
Yeah.
pretty straightforward.
Exactly. Now, in terms of writing them down, you'll see a few things.
Okay.
In printed stuff, you often see bold letters,
Okay.
like a bold F for force or a bold V for velocity. When you're writing them by hand, it's common to put a little arrow over the letter.
Okay.
So you might see like an F with a little arrow on top.
Got it.
Or sometimes you'll even see a bar underneath the letter. These are all just visual cues to remind you, hey, this isn't just a number, this has direction too.
This is a vector.
This is a vector.
Now, the material also mentions this idea of a line of action, which is described as an imaginary line.
Right.
What is the practical use of thinking about a force acting along this imaginary line?
Oh, the line of action is super helpful. Especially when things start to get complicated, imagine you've got your arrow representing the force.
Okay.
Extend that arrow forever in both directions. That's your line of action. Now, the neat thing is you can slide that force vector anywhere along that line without changing what it does to the object,
Okay.
as long as you don't change the length or the direction of the arrow itself.
Right.
This makes analyzing forces a lot easier because you can kind of move them around to a more convenient spot on that line.
So if I'm trying to figure out how a rope is pulling on a box, I can imagine that force acting anywhere along that rope.
Exactly.
Oh.
For the purpose of figuring out how the box moves. Now, the point of application is where that force actually touches the object.
Right.
And that matters if you're thinking about things like rotation. Like if you push a door close to the hinge, it's harder to open than if you push it further out.
Right.
Even if you're pushing with the same force.
So point of application matters for that.
Exactly. And then there are things called free vectors,
Okay.
like moments or torques, where the point of application doesn't really matter much at all for our purposes. You can move those around pretty freely and it doesn't change their effect.
Okay. All right. So we've got magnitude, which is like the strength, always a positive number or zero.
Yeah.
And then we've got direction, which is described relative to some reference, some coordinate system.
Yeah.
The material also mentions orientation and sense. And those sound pretty related to direction, but how are they different?
So they are ways of being more specific about the direction.
Okay.
Orientation is like the angle. Think about like a clock hand. Is it pointing at 12 o'clock, 3 o'clock, 7 o'clock?
Okay.
Sense tells you if it's going clockwise or counterclockwise.
Okay.
So let's say we've got something oriented at 3 o'clock. The sense could be towards 4 o'clock or towards 2 o'clock.
Got it.
Both are 3 o'clock orientation, but the sense is different.
So orientation is the angle and sense is kind of like the positive or negative along that angle.
You got it.
Okay.
That's a really good way to put it.
And this leads into how we can break down a vector into a unit vector and a scalar component.
Yeah, breaking it down.
So what are those exactly?
Okay, so a unit vector, think of it as like a pure direction. It has a length of 1, always. And no units, it's just direction.
Okay.
The scalar component, that's just a number, positive or negative, that tells you the size of the vector in that direction.
Got it.
So you can imagine any vector as a unit vector pointing the right way multiplied by a number to scale it up or down to the right size. And really important here, the scalar component, that can be negative.
Okay.
That's how we encode the sense.
Got it.
But the magnitude of the vector itself, that's always positive.
Okay.
Never negative.
That's a really clear way to think about it. Now, the material also mentioned that vectors can be constant, or they can change over time, depending on the situation. I guess that's pretty intuitive, right? Like wind speed and direction, that can change constantly.
Exactly.
So how do we deal with that variability?
Yeah. So a force might be constant, like a weight of an object, but it could also change over time. Think about like a rocket taking off.
Okay.
The thrust is increasing as it burns fuel.
Right.
So vectors are great for representing both things that are steady and things that are changing.
Both static and dynamic situations.
Exactly.
Okay. Now we've got a solid understanding of what vectors are. So let's start to think about how we actually work with them mathematically, starting with kind of the simplest case, one-dimensional vectors.
Right. Keeping it simple.
Yeah, so everything's lined up. How does that make things easier?
It makes them so much easier because we don't have to worry about like up, down, left, right, all that stuff.
Right.
We can basically treat vectors like regular numbers, but we slap on a plus or minus sign to indicate direction.
Okay.
So if we decide, let's say right is positive, anything pointing to the right's positive, anything pointing to the left is negative.
Okay.
And then adding and subtracting these one-dimensional vectors is just plus and minus.
Just basic arithmetic.
Basic arithmetic.
Exactly.
So if I have a force of 10 newtons pulling to the right and another force of 7 newtons pulling to the left along the same line, the total force is just 10 minus 7, which is 3 newtons to the right. That's exactly right. You found what's called the resultant vector.
Okay.
It's the overall effect of those individual vectors, those individual forces in this case.
Got it.
And even in this simple one-dimensional case, you can actually visualize this addition using what's called the tip-to-tail method. Imagine you take that 7 Newton force and you slide its tail up to the tip of the 10 Newton force.
Okay.
And then the overall effect, the resultant, goes from the very first tail to the very last tip.
Got it.
That's visually how you can see it.
Makes sense. And what about subtraction?
Subtraction is just adding the opposite.
Okay.
So if you've got vector A and you want to subtract vector B, you just flip the direction of B,
Okay.
make it point the other way,
Okay.
which in one dimension just means changing its sign.
Right.
Plus becomes minus, minus becomes plus, and then you add them up as usual.
They're finally multiplying a one-dimensional vector by a scalar that just changes its size, right?
Right. Exactly. Think of it as stretching or shrinking the arrow. If you multiply by a positive number, the direction stays the same, but the magnitude changes.
Okay.
If you multiply by a negative number, then it flips the direction
Okay.
and also changes the magnitude.
Got it.
Multiplying by -1 is just a fancy way of flipping the arrow around.
Got it.
Yeah.
Okay, that makes sense for when everything is in a straight line.
Right.
But things get more interesting when we move into two dimensions.
Yeah. Now we're talking.
Yeah, dealing with forces and motion in a plane.
Now we're getting into the real world here.
The material mentions using orthogonal coordinate systems. What makes those so useful for two-dimensional problems?
Okay, so orthogonal, that just means perpendicular.
Okay.
So the axes are at 90 degrees to each other. And that is super useful because it makes the directions independent.
Okay.
If you change something along one axis, it doesn't mess with what's happening along the other axis.
Okay.
And the point where they intersect, that's our origin, our reference point for everything we measure.
Now, we have different ways to describe things in two dimensions, like the familiar x and y coordinates,
Yeah.
and then polar coordinates, using distance and an angle.
Right.
So how do we choose which one to use?
It really depends on the problem.
Okay.
If you've got something moving horizontally and vertically, like a ball being thrown,
Okay.
x and y coordinates are usually the easiest.
Got it.
But if you've got something rotating or something where you care about the distance and angle from a central point, then polar coordinates are your friend.
Okay. So like a robot arm that's pivoting around a point.
Perfect example.
Yeah, okay. So sometimes it's more natural to think about the angle and the length of the arm rather than its x and y coordinates.
Exactly. It just simplifies things.
Now, the material mentions coordinate transformation. What's that all about?
So that's being able to switch back and forth between x and y and polar coordinates.
Okay.
Because sometimes you might be given a problem in one system, but it's easier to solve it in the other.
Got it.
So you got to know how to translate.
Okay.
And it's not that complicated. There are formulas for it.
So it's kind of like having a translator between different languages of location and direction.
That's a great way to put it.
Okay, we've navigated the plane, two dimensions. Let's think about three dimensions now.
Mm-hmm.
Entering the space around us.
Yeah.
How does that change things?
Well, we just add another axis,
Okay.
the z-axis, sticking straight up from the xy plane.
Okay.
Now every point needs 3 coordinates, x, y, and z.
Got it.
And vectors, they get a third component too. So instead of just like, fx, fy, it's fx, fy, z.
Okay.
3 numbers to tell you how strong the vector is in each of those directions.
Okay. And the material mentions right-handed coordinate system.
Yes.
Is that just a convention or does it have a deeper meaning?
It is a convention, but it's super important that we all agree on it
Okay.
to avoid confusion. So imagine using your right hand, your thumb, that's the positive x-axis,
Okay.
your index finger, that's the positive y-axis, and then your middle finger sticking straight out.
Okay.
That's the positive z-axis.
Got it.
That's how we make sure everyone's talking about the same thing.
Right. So we've got our x, y, and z, our 3 axes, and a single angle isn't enough to define a direction in space.
Okay.
So how do we deal with that? The material mentions direction cosine angles.
Yeah, so direction cosine angles are just the angles between the vector and each of the axes.
Yeah.
So you've got one angle between the vector and the x-axis, one between the vector and the axis, and one between the vector and the z-axis.
Okay.
Knowing those 3 angles tells you exactly where the vector is pointing in space.
Got it.
And the cosine of each angle tells you how much of the vector is pointing in that direction.
Okay. What about spherical and cylindrical coordinates in 3D?
Oh yeah, those are fun.
Yeah. When might we use those?
So spherical coordinates, those are great when you have things that are kind of radiating out from a central point,
Okay.
like the light from a bulb. You've got the distance from the center. You've got an angle like longitude and an angle kind of like latitude.
Okay.
Cylindrical coordinates, those are like polar coordinates, but with a height added on.
Okay.
They're good for things that are symmetrical around an axis.
Right.
Like imagine a can of soup.
Okay.
So you've got the distance from the central axis, the angle around that axis, and the height up and down the can.
Got it.
So it depends what you're trying to describe, which system is easiest to use.
So it seems like no matter which coordinate system we start with in 3D, we can always convert back to rectangular coordinates if we need to.
Absolutely.
I've
It's
heard-
all interconnected. You can go from one to the other pretty easily with a bit of math.
All right. Now let's delve a little deeper into unit vectors. We touched on them earlier. Why are they so useful when working with vectors?
Oh, unit vectors are great. I love them because they let us isolate the direction of a vector.
Okay.
Remember, they have a length of 1. No units. It's just pure direction. And we have special unit vectors that point along each axis.
All right.
I, j, and k
All right.
for x, y, and z.
Got it.
So any vector, you can break it down into how long it is, its magnitude, times a unit vector pointing in the right direction.
So if I know the direction I want a force to act in,
Yeah.
I can use a unit vector to describe that and then just scale it up by the strength of the force.
Exactly.
Okay.
Super useful when, 2 points on the line of action of a force. You can find the vector pointing from one point to the other, then shrink it down to a unit vector,
Okay.
and then multiply by the force magnitude.
Got it.
Boom, you got your force vector.
Now, are there any quick checks that we can do with unit vectors just to make sure we haven't made a mistake?
Oh, absolutely. Always good to check your work.
Yeah.
So first, the signs of the components of your unit vector, they should match the signs of the original vector because it's pointing in the same direction. And second, because it has a length of 1, each component of the unit vector has to be between -1 and 1.
Okay.
If you get a number bigger than 1 or smaller than -1, you know you messed up somewhere.
Got it.
Yeah.
Okay. Now, how do unit vectors relate to those direction cosine angles we talked about?
Oh, there's a direct link. The components of the unit vector are actually the cosines of those angles.
Okay.
So the x component of the unit vector is the cosine of the angle between the vector and the x-axis and so on.
Got it.
And there's a neat little trick.
Right.
If you square all 3 components of a unit vector and add them up, you always get 1.
Okay.
It's like a Pythagorean theorem for unit vectors.
Got it.
Yeah.
Okay, we're building a really solid foundation here. Now let's talk about vector addition.
Okay.
How do we combine multiple forces or other vector quantities to find their overall effect?
Yeah, how do we put them all together? So there are a few ways to do this. We've got the triangle rule and the parallelogram rule, which are really helpful visual tools.
Okay.
And they demonstrate this idea of the resultant vector,
Okay.
which is basically the single vector that has the same effect as all the individual vectors combined.
So if I have 2 friends pushing a box in slightly different directions,
Yeah, a classic physics problem.
yeah, the single force and direction that a box actually moves in, that's determined by the resultant vector,
Exactly.
which I could find using either the triangle rule or the parallelogram rule.
Okay. So the triangle rule, you take your 2 vectors, you put the tail of the second one at the tip of the first one, and then the resultant goes from the first tail to the second tip.
Okay.
Simple.
Makes sense.
Parallelogram rule, you put the tails together,
Mm-hmm.
complete the parallelogram,
Oh.
and the resultant is the diagonal going from the common tail to the opposite corner.
Okay.
It's the same thing, just a different picture.
Got it. Now, the material also mentions graphical vector addition and trigonometric vector addition.
Yeah, those can be useful sometimes.
Are these just like ways to visualize things, or do they have practical applications?
Well, so graphical addition, that's literally drawing the vectors to scale
Okay.
and then measuring the resultant. It's good for getting a general sense,
Okay.
but not super accurate.
Right.
Trigonometric addition that uses trigonometry,
Okay.
like cosine tangent,
Right.
to calculate the resultant more precisely, but it gets messy if you have more than 2 vectors.
Okay, so the most efficient way, especially when we're in 2 or 3 dimensions, is algebraic addition of components.
Yeah, that's the workhorse.
Okay. How does that work?
Okay, it's all about breaking things down. You take each vector and you split it into its components along the x and y axis,
Okay.
or x, y, and z if you're in 3D.
Okay.
And then you just add up the x components separately, the y components separately, and the z components if you have them. Those sums, those are the components of your resultant vector.
So it becomes just a series of simple additions.
Exactly.
Good.
So much easier than messing with angles and triangles and all that.
Got it.
Yeah.
And finally, what about vector subtraction? Does that still work the same way as in one dimension?
Yep, same idea. Subtracting is just adding the negative.
Okay.
So you flip the signs of the components of the vector you want to subtract, and then you add them up using any of those methods we talked about.
Got it.
Yeah.
Well, that was a really thorough deep dive into the world of vectors. We've covered what makes them different from scalars, how to visualize and represent them, and how to add and subtract them in 1, 2, and even 3 dimensions.
We really hit all the basics.
Yeah.
And as we mentioned before, these aren't just abstract concepts.
Right.
This is the foundation of how we understand forces, motion, so many things in the physical world.
It's all around us.
It's all around us.
Awesome.
Absolutely.
So whether we're talking about bridges or satellites, or even just how your phone knows which way is up, it all comes back to vectors.
Yeah, you don't realize how much you rely on vectors until you actually start learning about them.
Yeah, that's true.
It's pretty amazing.
So hopefully this deep dive has given you a clearer and more intuitive grasp of vectors.
Yeah, we hope you're feeling a little bit more comfortable with the idea now.
But this is really just the beginning. There's so much more to explore.
Oh, yeah, there are whole courses on vectors.
Right.
So we've just scratched the surface here.
And there are more advanced operations like the dot product and the cross product that we might delve into in a future deep dive.
Yeah, those are really powerful tools
Those are really cool.
for understanding things like work and energy and rotational motion.
Yeah.
So much more we can do with vectors.
We could do a whole series on vectors, probably.
Absolutely.
So to quickly recap, we look at the distinction between scalars and vectors,
The how much versus the how much in which way.
how vectors are represented both visually and mathematically, the usefulness of unit vectors in isolating direction.
Super handy, those unit vectors.
Yeah, very useful. And the fundamental methods for combining vectors through addition and subtraction. These are the building blocks for understanding a whole lot of phenomena in our universe.
Yeah, they're everywhere.
Thanks for diving deep with us today.
See you next time.
We'll see you on the next one.